Okay, so my talk is on classical verification of quantum computations. It's kind of in both areas of cryptography and quantum computing, and I'll try to keep it at a high level, but I would encourage a lot of questions during the talk. So, as you may have noticed, there's been a lot of interest recently in building quantum computers, and we're currently approaching an era in which we expect to have quantum devices with 50 to 100 noisy qubits. At this stage, we're not sure what computational problems these devices will be useful for, and that's currently a major algorithmic challenge. But what we are sure of is that we will no longer be able to classically simulate these devices. So given this, the question comes up of, if we can't classically simulate these devices, how can we test them? So how can we make sure that these quantum devices are behaving according to our predictions if we can't simulate their expected behavior? And in order to get a little bit more into this issue of testing quantum computers, I need to tell you why I say that it's hard to classically simulate them. And this has to do with the exponential scaling of quantum computing. So an n-qubit quantum system requires 2 to the n parameters to describe, because it's written as a superposition over bit strings of length n. And this fact by itself, the exponential size description, rules out classical simulation of quantum systems once they reach a certain size, because it's just not possible classically to hold this entire description of the quantum state. Now, even if we can't classically simulate these devices, in order to test them, we would have to be able to classically access some information about the quantum system. And the way to do that is through measurement, but this brings up another major obstacle. So due to a fundamental theorem in quantum information theory called Halevo's theorem, a classical measurement of a quantum system can reveal at most n bits of the system, even if the system itself requires 2 to the n parameters to describe. So what I'm saying is that quantum systems are not only exponentially complex, but also exponentially private. And because of this, the question of testing quantum computers is extremely difficult. So this question, it's a fundamental question, and it can be motivated from many different angles. And I'll start with the motivation from the perspective of near-term quantum devices, so these upcoming devices. Yeah?
Yeah, so when you say simulation, you just you don't define it at this point. You say to simulate. Whether would you classify simulate a quantum device?
Yeah.
You didn't define it. Should we take it as a vague term at this point, and later you tell us exactly what you mean?
No, I'm not going to focus on it. By classical simulation, I just mean, can a classical computer just describe the state of the quantum system at each stage and use this simulation to predict the final outcome? So what it would have to do is store this exponentially sized description of the quantum state. Yeah, so that's all I mean by simulation. And that's why I'm saying it's not practical. Okay, so this question of testing quantum computers, I'll start with looking at it through upcoming quantum devices. So as I said earlier, we're reaching an era in which we expect to have noisy quantum devices with 50 to 100 qubits. And in this era, our goal would be to reach this milestone called quantum supremacy. So quantum supremacy just means the experimental demonstration of a quantum speedup. So what it is, it's a task which is easy for quantum computers, but should be hard for classical computers. So we can experimentally demonstrate that a quantum system is performing this task, but we also have some theoretic evidence that it's hard for classical computers. And now, if we hope to reach this milestone, the first question that comes up is how will we know when we reach the milestone? Because from what I just said, this task should be hard for classical computers. So if we can't compute it using our current computing power, how can we actually verify that a quantum computer has reached this milestone of quantum supremacy? So this is the first area in which testing is extremely useful. And now, this question of quantum supremacy is an extremely interesting question, because if we could achieve quantum supremacy, it would serve as a test for quantum mechanics in the high complexity regime. So far what we've done is we've tested quantum mechanics in a low complexity regime, meaning essentially single particle dynamics. But if we could test quantum supremacy, we're testing quantum devices with upwards of 50 to 100 qubits. So we're testing them in the high complexity regime, which means we're testing this idea of exponential scaling. Now, this question is an extremely interesting and fundamental question, and it's garnered a lot of interest from industry. Yeah.
I think there are lots of multi-qubits experiments, but they are very structured.
Yeah.
You're probably talking about general computation as opposed to some particular Hamiltonian, which is regular and operates on a lattice.
Yeah.
I don't know, Schrödinger equation.
Okay. Yeah.
So, I guess physicists have done experiments in which there's a quantum mechanical process running on many bits, thousands and more.
Yeah.
But it's very regular as opposed
Right.
to making some strange things like a program does.
Yeah, like general quantum computations on a large number of qubits. Yeah. Okay, so this goal of quantum supremacy it's attracted industry attention because that's the next goal to reach with these upcoming quantum devices. But currently, we kind of have this strange strategy where, so before I said I want a task which is easy for quantum computers and hard for classical computers. But what's happening right now in industry is that they're going for tasks which are easy for quantum computers, but at the limit of classical supercomputer power. So the reason they're doing this is because once they pass this borderline region, then they can no longer verify the answers classically. So by doing quantum supremacy experiments in this regime, they can ask a quantum computer to perform the task, but they can actually verify it since it's still possible to compute with classical supercomputer power. But the problem with this kind of approach is that it requires a lot of assumptions. Because what they're saying here is there's this problem at the borderline of classical supercomputer power. So if we go anywhere past this borderline, it means that the quantum computer has surpassed the power of classical computers, but we can't check it anymore because we're past that line. So this is not ideal, and the reason we're doing this is because we don't know how to handle the issue of testing. And what an ideal quantum supremacy proposal would look like is as follows. So it should be easy for quantum computers, but computationally difficult for classical systems. And what that means is, when I say computationally difficult, I just mean we can argue that if a classical computer can perform this task, then it can solve some other problem we believe to be hard. And on top of this, even though it's difficult for classical computers, it should be easy to verify classically. So these are the two key properties we want, because then we can actually say that a quantum computer has performed this task, which is difficult for classical machines, which is the ideal notion of quantum supremacy. Yeah.
Factoring integers would satisfy this.
It would satisfy this, but I want this to work for upcoming quantum devices. So near-term devices with a small number of noisy qubits.
Okay, so it would be too easy factoring numbers of...
Yes, because that wouldn't be classically hard. So, okay, so that brings up what we've done. So in joint work with Zvika Bekersky, Paul Cristiano, Umesh Vazirani, and Tomas Vidic, we gave a proposal which satisfied the first two properties. So we're going along this ideal path, but there's a gap. And the gap is that our proposal is efficient for a quantum computer, but it's not efficient enough for near-term devices. So ideally, we would close that gap and make this proposal efficient for upcoming quantum devices, and then it would be an ideal proposal. And I'll talk a bit more about that at the end of the talk. Okay, so yeah.
So can you have the chain of tasks where you get rid of a couple of qubits at a time?
What does that mean?
So 100 qubit task that's easy for a classical computer and a 98 qubit system it can control. And then, so
yeah,
you get rid of quantifiers and AP equals to P space. So one at a time, basically.
I'm not quite sure how that proposal, yeah.
If you build a system with 100 qubits,
yeah,
if you could verify it with a system with 98 qubits on a classical computer, and then you could verify that system and so on.
I'm not sure that would test the scaling properly. If you verify it with a 98 qubit machine, how would that work?
No, it's just adjusting. It's you allow the verifier only the power of classical computation. It's suggesting that you allow it classical computation plus quantum but fewer bits.
Yeah, but we don't know how to do this reduction in between the steps. That's the problem with these.
It's a valid suggestion.
Yeah, it is a valid suggestion. We don't know how to do that reduction from like 100 to 98 to 96 to 94 to things like that. Yeah. Okay, so far I've talked about the question of testing with upcoming near-term quantum devices to reach the milestone of quantum supremacy. But this question of testing is relevant in a much more general setting. So once we pass verifiable quantum supremacy and we continue towards full-fledged quantum computation, the question of testing becomes even more relevant. And here what we're asking is if all efficient quantum computations can be verified classically. So once I ask this question, maybe the first thing that comes up is factoring. Now I'm asking about general quantum computations and not restricted to small devices. So why can't we just restrict them? Why can't we just test them using factoring? And the problem there is that factoring has this special property that it's easily checkable. In other words, it's an NP. And we don't expect that all quantum computations have this property. So factoring isn't a general solution to this problem. And we still require a general method in which we can verify, classically verify quantum computations. And now, when you think about this, maybe the immediate thing we should ask is whether there's a proof, like a quantum computer can produce a proof that a classical machine sees and can verify the quantum computation. So that's asking if, that's the same question as in NP. But instead of this, we can generalize it and ask if there's an interactive proof which can be used to verify quantum computations. So here you have a classical machine, which is the verifier, and a quantum machine, which is the prover. And the verifier's goal is to interact with this quantum machine in order to verify that the quantum computation has actually been performed properly. So in 2004, Daniel Gottesman asked this question of whether we can classically verify quantum computations in this interactive model. And to give you a bit more detail about interactive proofs, so the verifier's goal is to use the prover to verify the output of a quantum computation, but we generally model the prover as an arbitrary adversarial device. So the prover's goal is to kind of trick the verifier into accepting, even if he's lying. And the verifier, we should have the guarantee that the verifier can catch a cheating prover and can reject in that case.
You'll define it formally?
No.
Okay.
To define it formally, so you say that if the prover is reporting the honest answer, then the verifier should accept with high probability. And if the prover is reporting anything but the honest answer, the verifier should reject with high probability.
Anybody has questions on interactive proofs?
No. Okay, so since this question was stated in 2004, it's been extensively studied, but we studied it in two different models because we didn't know how to address this original model with a classical computer and a quantum prover, a classical verifier and a quantum prover. So in the first relaxation, the classical verifier was allowed access to a small quantum computer. So it was his own small quantum computer, and he could use this to test a much larger quantum computation. And here it was shown to be possible. The verifier could he could use this small quantum computer to send qubits to the quantum prover, and that was enough to allow him to verify a general quantum computation. And that was studied since 2008 in two different lines of work. And in one other model, the verifier was allowed to interact with two quantum provers rather than just one. And if you don't know about interactive proofs, the reason that two provers are more useful than one is, so you can think of the verifier as a police officer interrogating a prisoner. And if he can interrogate also the prisoner's collaborator and put him in a separate room, then it's much easier to verify the prisoner's story. So that's what's happening here. There's these two quantum provers who are separated. The verifier is interacting with both of them in order to verify a quantum computation. In the quantum setting, it's a little bit different because the quantum provers can share something called entanglement. So they can obtain non-classical correlations. And this both makes it easier for them to cheat, but also easier for the verifier to verify a quantum computation.
So they also, for the completeness, all the protocols use the entanglement.
We don't even know how to come up with a protocol which is complete without using entanglement. Well, I guess then you have a trivial protocol, but yeah. Okay, so these were the two previous models. And in my work, I went back to the classical verifier quantum prover model. And I showed that classical verification of quantum computations is possible in this model. But I do have an assumption. So I assume that the power of the quantum prover is limited, meaning that there are some problems that an efficient quantum computer cannot solve. And I'll talk a bit more about this in one slide, but for now all I'm saying is classical verification of quantum computations is possible, but I do need an assumption on the types of problems that a quantum computer is able to solve. Okay, so now I'll tell you more about what that means. In both the verifiable quantum supremacy and testing of general quantum computations, there's this underlying issue where you have a classical computer and you want him to test a quantum computer, but the classical computer is much weaker than the machine that he's trying to test. So how can he gain any leverage over a machine which is so much more powerful? And this is where I use the assumption that the quantum prover is polynomial time. And I use this assumption to say that there are certain problems that a quantum computer cannot solve. More specifically, there's some classical cryptography that a quantum computer cannot break. And this is called quantum secure classical cryptography. And the way to think of it is, so let's say there's a one-way function, and what I'm assuming is that an efficient quantum computer cannot invert this one-way function. So that's what I mean by it's secure against quantum computers. And more specifically, the assumption that I'll use is called learning with errors. It was introduced by Oded Regev in 2005. And essentially, when I say that learning with errors is secure against quantum computers, what I mean is that this learning with errors problem, which are noisy linear equations, cannot be solved by quantum computers. So this is probably the most well-studied classical cryptography, which is assumed to be secure against quantum computers, and this is what I'll be relying on for this result.
Well, we were saying that this is what the world will rely on if there are quantum computers,
Yeah.
we still want cryptography.
Yeah.
It's not just that your result relies on it, it's probably what the world will
Yeah.
need.
It's what pretty much everyone uses when they say quantum secure classical
If there
cryptography.
are quantum computers.
Yes. Yeah. Okay, so what I've said so far is that in order to classically test a quantum computer, I put an upper bound on the quantum prover. So I assume that he cannot solve this problem called learning with errors. But there's still an imbalance here because the quantum computer is still much more powerful than the classical computer. So what I'll do is I'll use cryptography to also boost the power of the classical computer. And the way that I do that is I give the classical machine access to something called a trapdoor. And this allows the classical machine to compute something that even the quantum machine cannot. So in the one-way function example, you can think of it as the trapdoor allows the classical machine to invert the one-way function. But since the quantum machine doesn't have access to the trapdoor, he can't invert the one-way function. So now what I've done is I've upper bounded the power of the quantum computer. I've said he can't invert the one-way function, but I've elevated the classical computer by giving him a trapdoor, and this kind of restores the balance between the two. And so this is a structure that I rely on to verify quantum computations. And now, the next thing I'm going to do is I'll spend some time on the actual cryptography that I'll use to do this, and they're called trapdoor claw-free functions. But are there any questions before I get into that? Yeah.
Just a point. The second part is not an assumption. The first one is an assumption.
Yeah.
The quantum computer cannot break learning with that.
Yeah.
The second, the verifier can do what he wants, so he can
Sure.
have a trapdoor. So I'm just pointing out the second part where you elevated the power.
Yeah.
You didn't really assume anything. That's
No. Yeah. It's the same assumption, the quantum. Okay, so now I can tell you about the cryptography that I'm going to use. And so these are called trapdoor claw-free functions. They were introduced by Goldwasser, Macaulay, and Revest in 1984. And a trapdoor claw-free function pair is a pair of functions which are injective and they have the same image. And there's a trapdoor which allows for efficient inversion. So given y, the trapdoor can be used to output the two pre-images of y. So it can produce the two pre-images of any image y. And now there's a claw-free property, which says that without the trapdoor, it is computationally difficult to find a claw. So if a machine does not have access to the trapdoor, it can't find any pair of pre-images x0 and x1 which map to the same point. And the reason it's called claw-free is because these two pre-images are referred to as a claw. So claw-free means that a machine which cannot break it cannot find a claw for any image y. And so I'm going to assume the existence of a trapdoor claw-free function pair which is secure against quantum machines. So a quantum machine cannot find a claw. Okay. Okay, any questions on this primitive? Yeah.
This is not separate from the assumption, but you can build this as long as you assume learning with errors is hard for quantum computation.
Yeah, so that's what I'll say later. So I can reduce this to saying, if learning with errors is hard for quantum computers, then there exists a trapdoor claw-free function pair, which is hard for quantum computers. Yeah. Okay, so this is a classical cryptographic primitive. They're just classical functions. But the reason they're interesting is because they're very useful in the quantum setting. So what a quantum machine can do is it can sample a random image Y and create a uniform superposition over the corresponding claw. So, okay, so the quantum machine isn't breaking the claw-free property. He's not finding both x0 and x1. He's just creating a superposition over them. And the way he does this is, it's pretty easy for the quantum computer. What he does is he creates a superposition over the domain, and then he evaluates the function in superposition. So in that second register, it says fb of x. So he either applies f0 or f1 to x, depending on that first bit b. And then he measures to obtain an image y. And once he does that, due to the entanglement in this state, the remaining registers collapse so that they are consistent with the image y that was measured.
So there's a measurement only of the last register?
Yes. So once that last register is measured to obtain y, the first two registers have to collapse so that they're consistent with y. And there's only two options for that, x0 and x1. So a quantum machine can do this only given access to evaluating the function. That's all he needs. Okay, so at this point, the quantum machine has just created a superposition. He hasn't gotten any information from it. Now, in order to get information from it, he has to measure the state. And he can measure the state in one of two bases. If he measures it in the standard basis, he'll obtain either one of the two pre-images with equal probability. So he'll obtain either x0 or x1, each with probability 1/2. And this isn't particularly useful because at this point, all the quantum machine has done is sampled a random pre-image image pair. And of course, that information is very easy to obtain classically as well. So far the quantum machine hasn't done anything that a classical machine could not do.
It's easy to obtain classically because I could pick a random x and
Yeah.
compute one of the f's on it. And get
Yes, yeah. Yeah, okay, so the point at which the quantum computer can do something different is if he measures this state in the Hadamard basis. So a Hadamard basis measurement is just a different type of measurement, and what it corresponds to is the quantum Fourier transform, or a reflection by pi by 8. And you don't have to understand the technical details of this, but the point is that if the quantum prover measures this superposition in the Hadamard basis, then he'll obtain a string D, which satisfies this equation. So the string D will be drawn uniformly at random, and it'll satisfy this equation. And so x0 XOR x1, that's the bitwise XOR of the two pre-images, and d dot x0 plus x1 is just the inner product mod 2.
So they're all n bit strings.
Yeah. Well, the output is just 1 bit because it's inner product mod 2. Okay, so this is the part where the quantum machine does something interesting because we don't know how to. What he's done is he's obtained a string D which is correlated to both members of the claw, but he doesn't actually know how to find the claw. And this is the kind of thing that we don't know how to do classically. And this is why trapdoor claw-free functions are so useful. And now what I'll do is I'll put this kind of structure into a protocol which I can use for verifiable quantum supremacy. So this protocol will have the property that a quantum computer can easily pass the verifier's checks, but a classical computer cannot. So now let me tell you how that protocol goes. Okay, the classical verifier selects a trapdoor claw-free function pair. He hangs onto the trapdoor and he sends the function pair over to the prover. Then he tells the prover to create a superposition over a claw and send back the image Y. And he does this, as I said before, by creating a uniform superposition over the domain and evaluating the function in superposition. Then the verifier chooses to test the prover at random. So he either asks him for a pre-image, or he asks him for a string D which satisfies this equation. Of course, the constraint is that the string D cannot be equal to 0. And now, if the prover had behaved honestly, and if he was a quantum machine and he created that superposition, he can pass the test very easily either way. If the verifier asks for a pre-image, he can measure the state in the standard basis and report the answer. If the verifier asks for a string D, he can measure the state in the Hadamard basis and report the answer. So this is a task which is very easy for a quantum machine to pass. And on top of all this, the verifier can actually check that the prover is passing the test properly, because the verifier can extract x0 and x1 and check that the string D satisfies this equation. So this is a protocol which a classical verifier can use to test a quantum prover, and so far what I've told you is that it's easy for the quantum prover to pass the test. And now what I need to tell you is why it's difficult for a classical computer to pass the test. So here's what would happen. If a classical computer could pass the test, then I can show that it essentially breaks the claw-free property. And this is because a classical computer can be rewound. So if a classical computer can pass both the pre-image test and the test for the string D, then what I can do is first run him on the pre-image test, extract a pre-image from him, then rewind him, extract a string D from him. And at this point, what he holds is both a pre-image, let's say x0, and a string D. But this string D and the image x0 reveals something about x1. And what I'll formalize in the next slide is why this is equivalent to breaking the claw. But the point here is that with the quantum machine, we can't run this rewinding trick because quantum machines cannot be rewound. So if a quantum machine is run on the pre-image challenge, and he measures the state in the standard basis, we can't rewind him and then do it again in the Hadamard basis. So this is a task which is very easy for quantum computers, but it appears to be difficult for classical computers, because if a classical computer could pass, it would hold too much information. So now let me formalize what I mean, like why this is hard for a classical computer. In this joint paper that I mentioned earlier, we built an approximate trapdoor claw-free function from learning with errors. And we use this construction to formalize the hardness of holding both the string D and the pre-image at once. So we showed that if a quantum or classical machine could hold both a pre-image and a string D, which satisfies this equation, then it is essentially breaking the claw-free property. And this is called a hardcore bit property, and it doesn't hold for general trapdoor claw-free functions, but it did hold specifically for our construction based on the properties of learning with errors. And it's crucial to the quantum supremacy proposal. So this hardcore bit property, it has two implications. The first is what I said on the last slide. If a machine can pass the verifier's check in the earlier proposal, it cannot be classical. Because if it was classical, I could rewind it, it could hold both things at once and violate the hardcore bit statement. And it's also a verifiable quantum supremacy proposal because it separates quantum and classical, and it's efficient to verify classically using the trapdoor. The next thing is that if a machine passes both tests, it cannot be deterministic. Because if it was a deterministic machine, then it could hold both the pre-image and the string D at once. And we use this property to generate certified randomness. So a classical verifier can use a quantum prover and this protocol to generate certifiable randomness that the verifier can actually check as random. And I'm also going to use this structure for verification of general devices, which I'll spend the rest of the talk on, and for something called homomorphic encryption. I won't cover that in this talk, but roughly homomorphic encryption is a protocol which allows a classical machine to delegate a computation to a quantum machine, and the quantum machine can run the computation, but he won't learn anything about the data while he's running it. So it's a blind delegation. Okay, now before I continue to verification, are there questions on this trapdoor claw-free structure?
This follows from the learning with the error assumption that you have such a hard code.
It doesn't follow directly, but yeah.
No, you proved it.
Yeah.
I mean, that's what you, It's not an extra assumption. Just
Yeah, it's still the learning with errors assumption. Okay, so now I can continue to verification of general quantum computations. So remember the question, I'm asking if classical computers can verify the result of quantum computations through interaction. And what I've shown you so far is that for verifiable quantum supremacy, I can use cryptography to create a task which separates quantum and classical machines. And here, for classical verification of quantum computations, I'm going to use a similar task, but it will serve a very different purpose. And the purpose it will serve is for classical commitment to quantum states. Now, let me tell you what classical commitment to quantum states means. So here's the ideal operation of how this classical commitment should look. The prover should select a quantum state of his choice and commit to it by sending a classical string to the verifier. Once the verifier receives the commitment, he asks the prover to measure the quantum state in two possible bases, either standard or Hadamard basis. And then the guarantee of the commitment should be that the prover's hands are cryptographically tied after he commits to the state. Meaning, once the verifier tells him to perform a measurement, he cannot change his mind. He's already committed to a state, he just has to measure the committed state in the basis requested by the verifier. So he cannot behave adaptively based on the verifier's measurement choice. Now, as you can imagine, this is a very powerful protocol because a classical computer is tying the hands of the quantum prover to a specific quantum state, and the quantum prover cannot change his mind after that. And this type of classical commitment is enough to verify general quantum computations, and I'll cover that in a couple slides, but right now I'll just tell you how this commitment works. Okay, so the prover wants to commit to a specific quantum state, and let's just say it's a single qubit state. And the way he does this is what he did earlier. He takes his state, he samples a random image Y, and entangles the state with the corresponding claw. And this is done exactly as it was before. So he begins with his state in a uniform superposition over the domain, and then he chooses to apply either F0 or F1 in superposition, depending on that first qubit. And then he measures that last register to obtain an image Y, and as a result of the measurement, the state collapses, so that the only elements remaining in superposition are the two pre-images of Y. Okay, this is it. This is how he commits to a quantum state, and the classical commitment is just the image Y. So here's what the commitment protocol looks like. The classical verifier selects trapdoor claw-free functions F0 and F1, and he tells the prover to commit to any state of his choice. The prover commits and returns the image Y.
It's the same commitment regardless of alpha 1 and alpha 0.
The commitment procedure is the same, yeah.
Not just procedure, the value Y is independent of alpha 0.
Because it's distributed uniformly at random. That's what you mean?
But also, yes. But, I mean, if alpha 0 and alpha 1 change to a different value,
Yeah.
Y would be. I mean, even knowing, you could not distinguish a state that the prover held in its hand, whether it's alpha 0 and alpha 1, or alpha 0
Yeah.
prime and alpha 1 prime, and Y was sent.
Yeah.
Y was sent.
Uh-huh.
You know.
Yeah.
So in what?
In what sense is this a commitment?
To the value, to the amplitude, yes.
Okay, so it's a commitment in the sense that once the prover is asked to perform a measurement on the state, he's going to be forced to measure that specific quantum state. And if he tries to measure anything else, then the verifier will either detect it, or there's some other, there's another equivalence there. Like, so what happens eventually is, okay, the goal is that this commitment ties the prover's hands to a specific quantum state. So
that's
yeah.
what you want to do. I'm just trying to understand why it happens if alpha 0 and alpha 1 were changed. Can you go to the previous slide?
Yeah, you mean that if they're changed after commitment, right? If you're saying that
We
yeah.
You're just two different provers, each one with alpha 0 and alpha 1, and another with beta 0 and beta 1.
Yeah.
It seems like they could, if they generated the same y,
Yeah.
not maybe I'll skip this and that.
The distribution of y is identical.
The distribution, of course, is identical.
Yeah.
I'm just saying, even conditioned on y.
It's
Whether we could distinguish.
cryptographical, it's
Yeah.
cryptographical commitment.
Yes, of course, but yeah, of course, but whether there is so there's an indistinguishability between alpha 0, alpha 1 and beta 0, beta 1, given y. So a different state would generate the same commitment string y.
Okay, so this commitment isn't used to force him to commit to a specific quantum state.
Yeah, that's the point I was trying to make.
Okay. The goal is for him to commit to any quantum state of his choice, but once he's asked for measurements, he cannot change his mind. So it's a different goal. So right now, I don't care about what state he chose. I just want to tie his hands to any state that he chose, and when I ask him for measurements, he has to measure that. And I'm going to tie this to the question of general verification in a second.
Also in the cryptography, also classically, when you commit, you have some string,
Yeah.
and it's also random. You commit to something.
Okay, so the point of this commitment, the reason why it works roughly, is because once the prover performs this commitment, he's taken his single qubit state, which he knew the full description of, and he's entangled it with this claw x0 and x1. And since the function is claw-free, the prover doesn't know the claw x0, x1, so he's taken this state and he's modified it to a form where he doesn't know what the state looks like anymore. And the point is that if he tried to change the state, so if he saw the verifier's next message and said, okay, now I'm going to change my commitment, he has no power because he doesn't even know what his state looks like. So if he tries to act on it, he won't know the result of his operation. And this is a rough intuition. I'm going to spend more time on this later in the talk. But so this is how the commitment procedure looks. And remember, so my goal was to cryptographically tie the hands of the prover, but not too much, because I still want him to be able to perform measurements if the verifier wants him to. So what this protocol does is it says that if the prover is not supposed to perform a measurement, he won't be able to do anything with his state. But if the verifier does want him to perform a measurement, then the verifier can help him perform the measurement. And the way he does that is that the verifier uses the trapdoor to extract x0 and x1. So now the verifier knows something about the prover's quantum state that the prover himself does not know. And now, using this information, the verifier can help the prover to perform a specific quantum operation on his state. And without this help, the prover cannot do anything to his quantum state. Okay, so this is the overall structure of the quantum commitment procedure. But now I'm going to step back and I'm going to link this to general verification of quantum computations, just to give you a picture of how everything fits together. And then to wrap up, I'll go back to this and I'll tell you why this second bullet point holds. So why it is that the prover is actually committed to a quantum state. Okay, so to tell you why it's enough to verify quantum computations, let's go back to the classical world for a second. And to verify an efficient classical computation, here's what a classical verifier can do. He can take the problem that he wants to verify it and reduce it to a 3-sat instance. The reason he can do this is because 3-sat is complete. And then once he reduces to a 3-sat instance, he can ask the prover for a satisfying assignment. And then once the prover gives him the satisfying assignment, he can actually verify that the assignment satisfies the instance. This kind of structure can be carried over directly to the quantum setting. And here's the analogy. So 3-sat corresponds to the local Hamiltonian problem. An n-bit variable assignment corresponds to an n-qubit quantum state. And the number of unsatisfied clauses corresponds to the energy of the quantum state with respect to the Hamiltonian.
Can you quickly say what's the local Hamiltonian problem?
Yeah, the local Hamiltonian, you're given a Hamiltonian, which is a Hermitian matrix. and you want to determine the energy, the ground energy of the Hamiltonian. So what that means is you want to determine the lowest eigenvalue.
So why is it called local?
Because you can write the Hamiltonian as a sum over a bunch of different matrices, and each matrix acts locally on only a small part of the state and acts as identity elsewhere.
Should identify local with the 3.
Yeah, I guess.
It's a bunch of terms that depend only on a few qubits each, and you just.
But the few might not be 3. But
no, it can be 3. Yeah, in fact. You can call it a 300.
Yeah. Okay, so this is the analogy, and now we can take this analogy and use it to show how a quantum verifier can verify a quantum computation. So what the quantum verifier does is he reduces to a local Hamiltonian instance H, and then he asks for the ground state, which is the same thing as a satisfying assignment. Then he verifies that the ground state has low enough energy with respect to the Hamiltonian. And this is why the verifier needs to be quantum, because he needs to verify that the state has low energy. And to do this, all he has to do is perform Hadamard or standard basis measurements. So what I'm saying is that the quantum verifier just asks for a quantum certificate, which is meant to be the ground state, and then he verifies that it's the ground state by performing Hadamard or standard basis measurements on this quantum certificate. And in my setting, what I want to do is get rid of this quantum verifier. And so now I'll replace it with a classical verifier. But the classical verifier wants to force the prover to perform the measurements that the quantum verifier would have. And of course, the problem here is if the classical verifier is telling the prover to do these measurements, the prover can change his state based on the measurements he's supposed to do. So he's not fixed to a specific quantum certificate. He can adaptively change the certificate based on the measurements. And this is where the commitment procedure comes in. So what I require is that first the prover should be classically committed to a quantum state, and then the verifier tells him, here are the measurements to verify the energy, and when the verifier tells him that, all he can do is measure his fixed committed state. And if this is the case, now it's equivalent to the previous setting with a quantum verifier. Because essentially what's happening is that there's this fixed quantum certificate, which is just being measured to verify the energy. So this is the link between classical commitment to quantum states and general verification of quantum computations. Yeah?
So again, why Hadamard measurement is enough? Why it's sufficient to measure the state according to in Hadamard basis?
It's a result.
It's a result. Yeah, it's not trivial.
So who is what the BLs?
It was Biamonte Love who did it first. Jacob Biamonte and Peter Love, I think. But actually, so even before that, I don't know if you know about this, but there's this Kitaev history state, and that's the actual ground state. And if you write out the Hamiltonian, which corresponds to this history state, that actually consists of terms, like these local terms, which can be verified just by Hadamard and standard basis measurements. And this is a byproduct of the universal gate set for quantum circuits. Yeah.
So this is done for the original state. You don't have to change the state to do that.
No. Yeah, just to get Hadamard and standard basis measurements, you don't have to change it. If I cared about locality, then you do have to change things. But for my protocol, I don't care about locality. For QMA verification, they do care. So. Yeah, so the ground state here is the original Kitaev history state. Yeah.
So does the verifier have to fix the basis before the committed scheme happens?
No, so what happens is, okay, when the quantum verifier performs a check, he receives the ground state and then he picks a random check. It's like...
Just for the measurement committed scheme. Just for the measurement, so it seems that the quantum the state that the prover held has been changed. It has been entangled with some other bits.
Right.
So it cannot perform a different basis measurement.
Yeah, that's what, okay, so this is what I briefly mentioned earlier. You're right. That's the exact problem. So here, once he performs the commitment, because of this entanglement, he can't do something like a Hadamard basis measurement. That's why it's a commitment, because it's tying his hands. But the next thing I said was that the verifier can help him perform the Hadamard. So I'm not going to get into that in this talk because it's too technical, but essentially what happens is the verifier wants him to perform a Hadamard on that original 1 qubit state, but he holds this large entangled state. So what he can do is he can perform a Hadamard on the entire thing, and the verifier can take that measurement and post-process it to get the Hadamard measurement result of the single qubit. So essentially the verifier can help him perform the Hadamard transform because the verifier knows x0 and x1. Yeah, if that didn't work, then I couldn't really do anything, because once he's committed to a state, he can't perform measurements. So that's a key part of the, yeah. Okay, so what I did so far is I linked this protocol to general verification of quantum computations. But now the remaining thing to do is go back to the commitment procedure and tell you why the second bullet point actually holds. So why is it that once the prover is committed, he's tied to that committed state and he can't change his mind? And to do this, I need to tell you, so this is called the soundness property of interactive proofs. It's just saying that the proof is secure. And to tell you why this works, I'm going to go back to the 2 previous models of verifying quantum computation. And in all of these models, the key difficulty is that the quantum prover has an exponentially large space. And in order to prove that he's doing what I want him to do, like that he committed to a state and he's measuring it, I have to characterize this exponentially large space. And in both of the previous protocols, this was also an issue. And the key step in these protocols was to enforce some type of structure in the prover's exponentially large space. So just as an example of what that means, in this protocol on the left, where the verifier had a small quantum computer, the way he enforced structure was that he just sent qubits to the quantum prover. So because he constructed the qubits himself, he knew that in some part of the prover's exponentially large space, there were these qubits, he knew exactly what they looked like, and he could use this characterization to force the prover to perform a general quantum computation. So that was the key part of the soundness proof there. And in my protocol, I still have to do this. I have to enforce some structure in the prover's state. But of course, I can't use previous techniques because the verifier doesn't have a small quantum computer and he's only interacting with one prover. So what I do instead is I change my commitment protocol to include something called a test round. And the goal of this test round is solely to characterize the prover's Hilbert space. So it's required, and I change the protocol just to characterize the space. And here's what it looks like. So remember, the verifier sends over some functions and reports an image y. And to test him, he just asks the prover to report a pre-image of y. And if the prover behaved honestly and actually committed to a quantum state, then it's very easy because he could just measure that state in the standard basis and he would obtain a pre-image. So he'll always pass the verifier's test. But what I need to say is something more general. So I need to say that this test can be used to characterize the state of an arbitrary prover no matter how he cheated. And the way I do that is, so if the prover is passing this test, then in order to obtain this pre-image, he measured some part of his space. So that means at some point in time, in some part of the prover's space, he must have held pre-images of y. Regardless of how he cheats, as long as he passes the test, then I can say this. So in other words, I'm saying at some point in time, I can write his state in this format. And the only thing to notice about this format is that it's a superposition over the 2 pre-images, x0 and x1. And the rest of it, like the psi notation, that's just supposed to represent the rest of his space, which is very large. But all I'm saying is that at some point in time, in some register, he held a pre-image of y. And this is exactly what the test gives me. And now the reason this is so useful is because before this step, for an arbitrary cheating prover, I wanted him to commit to a state. But of course he has an exponentially large space. I didn't even know if he held a quantum state. He could have just been giving the verifier arbitrary classical distributions. But what this is saying is there is a committed quantum state, and I'll call this the specific quantum committed state. So this test, it seems simple, but it's actually very powerful because it's allowing us to say that the prover held this quantum state which has some form that we know about. And now what I need to do is I need to take this characterization of this committed state and say that once the verifier asks the prover for measurements, this is the state that he measures. So this first step was just to say that he held a committed state, and now I need to argue that his hands are tied to this specific committed state. Okay, so the reason this holds is roughly the intuition I gave earlier. It's because this committed state is not known to the prover. He doesn't know the full description of it because it contains x0 and x1. And the prover does not know that because that's a claw. So roughly, if the prover tried to deviate, like if he tried to apply some operator to his state after commitment, then he's acting blindly. Like, he doesn't know how his action will change the state because he doesn't even know what the state looks like. So this is the key step. And then what I argue is I use the cryptography to say that his deviation is so limited, meaning he really can't tell what's going on at all, that instead of deviating, so instead of changing the state after commitment, he could equivalently have committed to a different quantum state and then perform the measurements honestly. So to prove this, the second bullet point, I have to characterize any deviation he applies and say that this deviation is so restricted that it satisfies this property. And to characterize the deviation, I require like this hardcore bit and the claw-free property. And this is these two, that last bullet point is the majority of the soundness proof.
So what is the formal meaning of the second one? That for every cheating prover, there is another prover
Yeah.
that is actually operating on the original,
Yeah.
not this real state, but the actual states that will result of
Yes.
an actual measurement of
Yeah.
the registry.
Yeah, there's another cheating prover for whom there exists a quantum state which he commits to and then measures honestly. That's all. So every cheating prover can be modeled by another prover who's just committing and measuring. So that's the commitment guarantee. Yeah.
So what happens if the prover doesn't really have this state, but rather something that contains this state with some low probability, and tries to pass the test with low probability, which is still not
Right. Okay, so you're just saying he's passing the test with low probability. So this characterization was for someone who's passing it perfectly. For that, I can say that this prover is within some trace distance of a prover who's passing perfectly. So it's a robustness claim. So take an arbitrary prover, say he passes with probability 1 minus p, then he's within trace distance, say something like 1 minus p, of a prover who passes perfectly. And then I characterize the prover who passes perfectly.
But,
Yeah.
but if I only want to pass with negligible, so you need some machinery at the end to reduce the probability of error, to kind of to increase the soundness.
Yeah. My soundness is 1/2, so it's not great. But if yours only passes with negligible probability, then it's not going to affect my sound. Yeah. Yeah.
And also, you're saying that this is actually the state, I guess. So in principle, the prover can measure something else and then do some computation over it. So,
Yeah.
so it's not exactly this state, but maybe something equivalent to this state.
Yeah. That's always the condition. So what you say is his state is unitarily equivalent to this, up to some unitary transform. Yeah. So of course I can't say that this is the state, but what I say instead is that there is a prover who holds this state and produces the same outcomes as our original prover.
So it's like without loss of generality.
Yeah. Yeah. Okay, so I think this is it for the verification results. So are there any more questions? Okay, so what I showed was that quantum secure classical cryptography can be used to test quantum computers. And more specifically, the cryptographic primitive I relied on were trapdoor claw-free functions, which I said could be built from learning with errors. And the reason that these were so useful is because the quantum machine could use these functions to create this secret state which is unknown to him. And this state is the superposition over a claw. And the fact that the quantum computer did not know the state could be used to verify general quantum computations. And so I said that the structure could be used for verifiable quantum supremacy, classical verification of quantum computations and for quantum homomorphic encryption, although I didn't talk about the last result. And now there are some open questions. The first is what I mentioned early on in the talk. So I said we have a verifiable quantum supremacy proposal, which is easy for quantum computers, hard for classical computers, and efficiently classically verifiable. But we do want to improve it so that it is more efficient for quantum computers, meaning we want it to be implementable on near-term quantum devices. And so right now, just with basic estimates, we estimated that it would take a couple thousand qubits. But our goal would be to use a more streamlined learning with errors implementation, so to talk to cryptographers, to try to get this down to several hundred qubits, which would work on upcoming quantum devices. And this question is interesting because it would involve a collaboration between cryptographers and experimentalists working on quantum computers to see how we could make this actually practically feasible within the next, for the upcoming devices. And the other question that I'm particularly interested in is information theoretic verification. So what I said was that classical verification of quantum computations is possible, assuming that learning with errors is secure against quantum machines. So I had this assumption. But another thing that we could do that we don't know is impossible is we could take away this assumption. So we could say that we're not putting any bound on the quantum prover, but we still have a protocol which could verify quantum computations. So the honest prover would be an efficient quantum computation, but a cheating prover could be all-powerful, and the verifier should still be able to catch him. So this seems like a pretty interesting question because my current results tie together quantum computation and classical cryptography, but there we would have to use techniques from classical complexity theory to try to solve this question. Okay, so that's all. Thank you.